Welcome to the Integrated Engineering 170, Section 312, Team 3, the Pedal Pioneers. For this project, our client, Jason Joe, wanted an updated pedal system for the university's desktop car simulator. Our team set out to replace the current system, a repurposed video gaming rig with a custom design that had more realistic pedal geometry and functions.
Our design needed to register as a video game controller when plugged into the simulator via USB, and it also needed to interface with the custom dashboard and gear shifter to register and display acceleration and deceleration accurately with the pressing of the pedals. With regard to physical form, Mr. Joe wanted the brake pedal to be suspended from the ceiling of the frame, whereas the gas pedal was to be attached to the floor, independent from one another in their mechanisms. Because the system is intended for a desktop simulator, he also requested that the frame be portable.
After creating our 6 preliminary designs, we compared them against each other within a design matrix, from which the rear rod brake design and the chip clip gas design emerged victorious. The first change came when we determined that the PVC frame would be too flimsy, so we switched to one made out of plywood and 2x4 wood. Then we soon discovered that the arc motion of the suspended brake pedal made the rear rod impractical. Accordingly, the linear potentiometer was replaced with a dial potentiometer, and a torsion spring was substituted for the extension spring. Next, we added a gear system to attach the brake pedal to the potentiometer in order to amplify the minimal rotational movement.
The gas pedal still uses torsion springs like the original design, but in order to attach it to the frame, we added a hinge so we could have something to screw into. Our next problem occurred when we couldn't find a practical way to attach a dial or linear potentiometer, so we switched to a Hall effect sensor, which measures the strength of a magnetic field. Finally, both systems also needed an eye hook and rod system to keep the torsion springs from rising as the pedals were pressed.
For the first prototype, we used the laser cutter to cut the C-shapes for the frame out of a high-density foam board. We then used a chop saw to cut a 2x4 plank, which we screwed between the C-shapes. Then we used a drop saw to cut a PVC crossbar, which was also added to the frame. 3D printing was used to fabricate both pedals and the gear for the potentiometer. For the final prototype, we used the CNC router to cut the frame C-shapes out of plywood. After that, we used the bandsaw to cut a dowel rod crossbar, which replaced the PVC. We used the same method as before to cut more 2x4 planks and a drill to put the frame together. Then we also used a table saw to cut the plywood base and then attached the pedals to the frame. The brake pedal was slid onto the dowel rod and the gas pedal was screwed to the plywood base. We also used a drill to attach the eye hook and rod system for the torsion spring.
The brake pedal hangs freely from the dowel rod, and physical resistance is provided by a torsion spring, where one leg is flush to the rear of the pedal arm and the other is inserted into the 2x4. A 3D printed rod holds the dial potentiometer at an appropriate length for its gear to match with the teeth on the brake pedal. The hinge built into the gas pedal secures it to the base. The torsion springs are slid into the gas pedal and rest on the hinge with another eye hook and rod system to keep the springs in place.
There is a magnet attached to the plywood base with a Hall effect sensor on the underside of the gas pedal. When the pedals are pressed, the torsion spring provides physical resistance as the pedal turns. This changes how much the dial potentiometer turns or how far the magnet is from the sensor. This displacement changes the voltage, which is read by the Arduino. After pressure is removed from the torsion springs, both the pedal and the electronic components return to their original positions. Finally, unbalanced motors nested in holes in the back of each pedal can be programmed to activate when prompted by the simulator, causing a vibration strong enough to be felt by the user.